Hello, everyone. Welcome back to Python Challenge for All. So let's see, we've been working with the Fibonacci sequence, Fibonacci numbers. The first approach was very slow. In contrast, the second approach with memoization was very fast. I hope you like that demonstration or your computation and comparison of the computational speed, which sometimes called complexity, computational complexity of the algorithms. Okay, so today, as we have we have done lesson up to 100. So today is the lesson 101 coffee break. Okay, so I'll give you some trivia about Fibonacci numbers. So one is that, as I mentioned several lessons before, the ratio of consecutive Fibonacci numbers, which means how fast it grows one by one, okay? Growth speed. Did you try to find out? What does the ratio of consecutive Fibonacci numbers converge to? So let's continue, go back to the code and see. Okay. So for example, no, not necessarily fact one. What we want is fib1. But since fib1 is slow, we might want to use fib2. And let's see how it works. Fib2 is like this, right? So to do that, we can use all the way down to see the ratio of consecutive or adjacent consecutive numbers. For example, what we want is for, say, I in range. Okay, what is this? For I in range, say, let's see, up to say 40. Let's try this. And we can print I, and then yeah, value is F is, yeah, as we noticed, we need to initialize the L list each time we compute values. So we do L01, and F value is fib2 times I. Okay? Maybe we might want 1I, but anyway. So we can start, say, from 2, because we don't want very small values. Okay, we might want to start with 2, and each time calculate fib of I, and then, okay, print fib f value, and also okay, fib 2, right? We don't need this. We need this at the beginning. And then fib2, let's see, just simply write the values fib2I, and then fib2I divided by fib2I minus 1. Okay, so let's see what values we have by computing these values. Okay, so 2, 3, 4, 5, 6, all the way it seems we're approaching something. 1.618033988749. Yes, okay. Some people might know this. This is what we call golden ratio. Golden ratio is, for example, in this case, A plus B, the ratio of A plus B over A is equal to the ratio of A over B, which is called, sometimes noted as phi in Greek letter. and which is equal to 1 plus square root of 5, all divided by 2, which is 1.18 something. Okay, which is this. So let's calculate that it is exactly this number. So what we want is, as I wrote, 1 plus math dot square root. Yeah, we don't need mathematics here. Did you know that we can calculate square root of 5 by 5 raised to the power of 0.5, which calculates the square root of 5, all divided by 2. Okay, let's continue. Let's calculate this. Okay, this gives 1.61803. So exactly this number. Okay, so as you know, this number goes to golden ratio. Yeah, if you see this, you might find if you look into, say, any internet materials, you can see the interesting stories of golden ratio and Fibonacci. Here comes Fibonacci numbers or golden ratio, and all in these things, because we human beings sense that golden ratio is very beautiful, stable and beautiful. Another trivia is that there is a closed form expression for Fibonacci numbers. So to calculate any Fibonacci number, there's a closed form expression, this. Although this contains square root 5 and powers of those numbers, strangely, this always produces natural numbers starting from, as usual, 0, 1, 2, 3, 2, 3, 5, 8, something like that. Yeah, this is also written as this phi, using the same phi as here. Please check yourself if you are interested. Okay? So phi to the power of n minus, yeah, we can calculate this, but I don't do this time. Okay. Interesting. Maybe we might want to try it now. That's right. So let's try this for, again, n equals I in range 20. Let's write this way. So print I, and what we have is, let's call this number, okay, let's call this number phi. Phi equals this number. And then what we want is, as we saw in this one, phi to the power of n minus this one. So phi to the power of n minus 1 minus phi raised to the power of n, all divided by square root of 5. So all divided by 5 to the power of 0.5. Okay, let's calculate this and see what produces. N is not defined. Sorry, it's not n. It should be not I, but n. Okay, so it's a very close approximation of all these Fibonacci numbers. 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89. Yeah, there's some error because this is a numerical approximation. But yeah, as you can see, these numbers are very close to the correct Fibonacci numbers. Of course, I should write n here instead of I. Okay, 19th is 4181, which is exactly what we got here. we didn't have it, but 40 is like this number, and Or yeah, okay. 8, sorry, 20 is, I should compute. Oh, yeah, okay. We should compute up to, say, 30, 31 to see more approximations. So 30 is like this number, uh, 832,040. 8,200, yeah, exactly the same as this, or much previously here. Okay, good. Lastly, drawing Fibonacci squares. So yeah, as you can see, this is what we call Fibonacci squares. Um, so it's like the what you see in Nautilus shell, and each side is Fibonacci numbers connected to each other. So let me draw this for fun using turtle graphics. It's only fun and my favorite um, pastime to draw. So to use, as you know, if you remember, uh, pip install ColabTurtle. Okay, let's import it. Let's uh, install, and in the meantime, let's import ColabTurtle. ColabTurtle as t. Maybe this is simple enough. T and t dot initialize turtle, and maybe you can specify speed here, and let's just see what happens for the loop smaller than for n in range. Say 10, and for I, because we need to write several more than 4 squares, we write 6 sides rather than 4 sides of each squares. So if I is smaller than 4, or smaller than equal to 4, the pen should be down. Else, pen should be up. Okay? And it's simple. Okay? Go to forward, fib 1, fib 2, n times 5, for example. Okay? And then t right by 90 degrees. This is all for drawing 1. And then left 90 degrees. Okay, let's see how it looks like. Oh, sorry, I should write ColabTurtle.Turtle as t, and then t.initializeTurtle 8. Let's run it. Okay, it's running. You see how the turtle is drawing spirals. Okay, let's do it a little more than this by changing, say, up to 15. And also, let's change the pen width to 1. And I think this is good enough. Let's run it again. Okay, it's working. Yeah, okay. Maybe we can write the value at the corner. to see that which number is that. So 1, 2, 3, 5, 8, 13, 21, 34. Yeah, like that. So although the canvas is too small, we can see that it is drawing the Fibonacci squares like this. Okay, I hope you like this and try yourself and enjoy the turtle drawing with Fibonacci numbers. Okay, that's all for today. Please come back next time. Bye-bye.